Okay, so yesterday we discussed about we started with the topic of time response analysis and also the specifications, and we started with the first order system. And in the first order system, we identify that how the specifications uh, depend upon the pole of the transfer function. So we determine the settling time, the rise time, and the time constant also. Now today we'll discuss the second order system. So the same concepts of poles and zeros and the transient response we will extend now for the second order system. So for the first order system, we saw that the response was pretty much simple, but the second order system exhibits a number of responses, or it has different types of responses, and and in fact, depending on the location of the poles and zeros, all those responses are different. For example, if we see one transfer function, let's say, hmm, we have this b upon s square plus as plus b, and with the step response we want to see in C of s, where the input is a step signal. Okay, so here you see that the system is second order because the denominator is of second order polynomial, and we have b upon s square plus as plus b. Okay, so now substituting or considering some particular values of a and b, which basically determine the location of the poles. So in the first part, we let's say we put it to a and b both as 9. Okay, in that case we would have s square plus ns plus 9, 9s plus 9, and the poles are located on the real axis onto the left hand side. So since the poles are located on the left hand side, we know that the system is stable. And if you compute the time domain response by taking the Laplace inverse of this C of s, multiplying this transfer function and by 1 upon s, you would obtain this kind of response. And you would notice that this response is quite similar to the response we had seen yesterday, that is the first order response. Okay, now for another location of poles and zeros, we put a is equal to 2 and b is equal to 9. That is to say, we put the location of the pole still onto the left hand side, as I said yesterday, that we will consider only the stable plants. For the unstable plants, it doesn't make any sense to study these responses. Okay, so on again on the left hand side, but this time the poles are located, or poles are the complex poles. Okay, and the complex conjugate poles. So for these location of poles, this is the response you would obtain. You can compute it by taking again the Laplace inverse, and the if you plot this response, you would get this one. Okay, and we call it the underdamped response. And the above response, which was looking almost like a first order system, we call it the overdamped response. Okay, now in another example, if I put a is equal to 0 and b is equal to 9 to obtain this transfer function 9 upon s square plus 9. So this is to say that we have the complex conjugate poles, but those poles are now located on the imaginary axis. So since the poles are located on the imaginary axis, we expect it to behave like some sort of sinusoidal signal, and in this case we have 1 minus cos 3 of t. And these responses are also called the underdamped response. And another response we have is where we put a is equal to 6 and b is equal to 9 to see that the poles are located on the real axis, and these are the repeated roots. Okay, repeated roots at minus 3. So this response you would obtain, and again it appears like a first order system, and we call these the critically damped systems. Because if you have the repeated poles at minus 3, it is basically saying that you have 1 upon s minus 3 and s minus 3. So it is like a cascade connection of 2 oh sorry s plus 3 and s plus 3. Okay, it is basically saying it's a cascade connection of two first order systems, and that's why you are obtaining this behavior like of a first order system. Okay, so these are the different responses. So if I quickly summarize, if we quickly summarize, we have the type of responses what we call the overdamped response, the underdamped response, and the underdamped response we see two types of response where the signal is settling on the real axis, I mean settling at some fixed value, but here it's an oscillatory signal. Okay, we will come on to see what is the difference between these two responses, the underdamped responses, in which one is behaving like an oscillator and another is behaving or settling down at some steady state value. Okay, and the third response is your critically damped response. Okay, the critically damped and the over damped, they almost like a first order system. Okay, we will also see that how these two the first order type of response is different. Okay, so starting with the again the generic representation of the second order system, similar to what we have done yesterday for the first order system. So in the forward path we have the transfer function omega n square divided by s upon s plus 2 xi omega n, and this is connected in the feedback path. Okay, uh, so let me see, there is one question is regarding again here the numerator is taken as b, which is same as the constant term in denominator. Yes, particularly for the second order system, you would see it is just for the simple representation of the system, because normally the performance specification is only concerned with the location of the poles. There could be other values, but you can reparameterize it. We will see this while solving some numerical problems, and in fact you can see in some tutorial problems also that in some problems it the numerator, let's say, might not be similar, or some, or let's say the coefficients of the numerator is not same as the denominator coefficients. Okay, you can reparameterize it. This is just for the simple representation. Okay, so we have the forward path transfer function is ys over es omega n square upon ss plus 2 xi omega n, and if I see the overall closed loop system, if I see the overall closed loop system from R to Y, this map, and this map is let's call it the G. So this G is basically, we obtain this one, omega n square divided by s square plus 2 xi omega ns plus omega n square. Okay, we will see that why we have specified this omega n xi, what is the role of xi, because whatever the transfer functions we had seen in the previous example, for different values of a and b, you could obtain for different values of zeta and omega n. Okay, so if I write that transfer function once again, we have this b upon s square plus as plus b. So this is what we have considered in a generic form, right, where b is our omega n square and a is your 2 xi omega n. Okay, so now substituting this r as 1 by s, because we are interested in the unit step response, in that case we would have our y of s as the multiplication of rs and the overall transfer function. So for this function, we can take the Laplace inverse to finally compute this y of t. So this y of t is containing again some force response and the natural response. Okay, and in this case we have 1 minus e to the power minus xi omega n t divided by 1 minus xi square times sine of omega n 1 minus xi square under root t plus cos inverse psi. Okay, so this is the generic solution of the second order system. Now we have introduced now we have introduced some other parameters where we say for xi and omega n. So we will see the significance of this xi omega n separately. So now in this case, as you see, as xi decreases, as the value of xi decreases, you would have the large overshoots, and this is what we had seen in the previous couple of examples. So here let's write it once again, where we have this a is equal to 2 xi. Okay, and from here we have xi is equal to a by 2. So all these 9, 2, and here we have the 0. Okay, so in all these b c d we have the value of xi, the decreasing value. So you notice that now we are having more overshoots. So by the overshoots we define that, let's say we have the step response, the step signal, and the value above this of the response above this 1 magnitude line is basically we have defined the overshoot. So you see that as the value of xi is being decreased, we have the overshoot, prevailing overshoots in the responses. Okay, and for xi is equal to 0 we had no damping, similar to the uh, example where we have the purely oscillatory behavior. Now in the second point, when we have xi greater than or equal to 1, then we would have no overshoots. Okay, again you can refer to the example and we call those responses as the overdamped response. Okay, so now we are defining those different type of responses: overdamped response, underdamped response, and critically damped response in terms of the value of the parameter xi. Okay, so if you want to recall this for xi greater than equal to 1, here we have xi greater than equal to 1. Okay, in the b part. So for this we have no overshoots. Similarly, here we have xi greater than 1 in the e part. Hmm? Again we don't have any overshoots. Okay, now let's compute the roots of this transfer function. So the roots of the closed loop transfer functions, there would be two roots because this is the second order system, and we have minus xi omega n plus minus j omega n under root 1 minus xi square. Okay, and we can substitute or we can represent them as minus alpha plus minus j omega, where alpha is xi omega n and omega is omega n under root 1 minus xi square. Okay, so here one important point to introduce this alpha and omega is that alpha controls the rate of the rise or decay of the unit step response, or alpha controls the damping of the system. We will see. So we call it alpha as the damping constant or the damping factor. Now when both these poles or both these roots becomes same, or saying that xi is equal to 1. Only for xi is equal to 1 we would have s1 is equal to s2. Okay, so those responses are called the critically damped response, as we had seen in the previous example, and for that we will have only alpha is equal to omega n. So we can compute the damping ratio xi as alpha by omega n, which is the damping ratio, and this we define parameter xi as the damping ratio then. Okay, because it controls the damping of the system. Okay. Now let's see the response of the second order system for different values of psi. So when xi become equal to 0, let's write this response once again. Okay, so I think you can see the response here. So when xi become equal to 0, we have the purely sinusoidal response as expected in the as we have seen in the previous example. When xi becomes equal to 1, we have yt is equal to this, so we have two exponential terms which are decaying. When xi is between 0 and 1, I haven't write the response, but you can compute the response. And for xi greater than 1, we have this bit complex appearing the response. But it's not so complex because these terms are the some constant terms, and these is the roots of the polynomial. Okay, so we have only some exponential terms and one is the first term, 1. So this response would almost appear as the first order response. So in the last case, so since it is the overdamped because of the xi greater than 1, the unit step response of the second order system will never reach the step input in the steady state. Okay, we will see how. So xi, we had seen the significance of xi as it is the damping ratio which controls the damping of the system. Now there was another parameter which we define as the omega n, and we define it as the natural undamped frequency. Meaning to say when xi is not equal to 0, the response of yt is not a periodic function, and omega is not a frequency. So the point here is that you should not confuse this when we define this omega n as the frequency term. It is not a frequency in its usual sense. Okay, because we had seen that the response of yt is not a periodic function. It is a periodic function only when xi becomes equal to 0. Okay, and if you see the response or the roots, particularly this one, so if xi becomes equal to 0 in this case, so the roots we would have this part would be 0, and we would have xi inside the under root, it become 1, and finally we would have plus minus j of omega n. Okay, and if we take this term, this is nothing but omega becomes equal to omega n. So this frequency what we have defined becomes equal to the natural frequency, and the system response would be an oscillator with this natural frequency. So this is the reason we are defining this as the undamped frequency, because omega as it appearing into the roots of the closed loop system is not a frequency in its natural sense. So that this is the reason sometimes we define as the conditional frequency or the damped frequency. Because for the undamped frequency omega n is a frequency in its natural sense. Mhm. What you are saying, just repeat me so that I can write. B. So let's just a minute. So we have the generic representation as B upon S square plus AS plus B. Okay, so I will represent it with another variable. Let's say C. Okay, if B become equal to 0, then I would have C upon S square plus AS. Okay. Yes, in this case, we can in fact represent this as S upon S plus A. First order system with an integrator. Yes, it is all. Yes, it is always a second order system. Yes, because we are having this S square. Uh, no, in fact, you can analyze these systems also in the sense, because if I see the location of the roots of this closed loop function, we have s is equal to 0 and s is equal to minus a. Okay, so both the roots are located onto the real axis. One is on the origin and another is in minus a. So if we see the some of the previous responses, so it might appear as this one. Okay, where this pole is now located here and some other pole is located at minus a. Because generally when you have the pole at the origin, so it behaves as an integrator, and with an integrator you see that it would always increase, right? So generally we do not we will come onto this thing when we have the a pole at the origin. Okay, so now coming on to the classification of the system dynamics with respect of the damping ratios I. So just to summarize that if we have xi between 0 and 1, we would have S1 and S2 as these poles, where minus I omega n is less than 0. So we have this underdamped response. When S1 and S2 is at the repeated roots, where we have the xi is equal to 1, we call it the critically damped. For xi greater than 1, we won't be having the imaginary terms here. So those responses are called the overdamped response. And psi is equal to 0, we have plus minus j omega n, meaning to say poles located only on the imaginary axis, we have the undamped response. And for xi less than 0, we have that minus xi omega n greater than 0. So those responses are called the negatively damped response. Okay, because if minus xi omega n is greater than 0, then you can expect that where the location of the pole is. Okay, so on the S plane, so this is the S plane. On the S planes, if we have this real S and the imaginary S, so all this part what you are seeing here is the unstable response. If the poles are located here in this region or in this region, meaning to say these are the complex conjugate poles, and then we call it the underdamped response. And for the poles located on the real axis, we call it the overall overdamped or the critically damped. Okay, so similarly, in one of the example what we had seen here, this critically damped response. Okay, so I think we can take this performance specifications into the into our next discussion about the maximum overshoots or the performance specifications related to the second order system. Okay, so